So let's talk about modeling and simulation today. And before even starting out with the basic topics, we want to cover what is simulation and what is modeling. So simulation is basically simulating a system, right? What is a system? Any system, right? So for example, um, you want to simulate your classroom environment. Maybe you will make a software system for that where there are students and where there's a teacher and there's an interaction between them, right? In this case, the way you make the model, the whole model process is called the modeling, right? The way you make the model. And what is simulation? It is experimentation. Like maybe I put two teachers in my software to see how the students will, react to it, or maybe I can decrease the number of students in my classroom. So modeling is how we make the model, and simulation is we are changing variables inside the classroom to see the different reactions, right? This is modeling and simulation, right? Now let's talk about what kind of systems we can simulate or, we can basically model, right? And it is a book by Bangarts, right, which I'm taking into context to understand about the simulation and modeling. Okay, so these are the type of systems here that we are going to study, and there are like 6 types being described here. Okay, so first of all, we have what is a system in general, right? A system is just a particular environmental phenomena, right? I'm teaching you, you are watching this video, it's also a system, right? We are basically in a classroom setting, so that's a system too. Not really, but yeah, we can call that. We have, when we are going to an office or when we are going for a bank to get some money or deposit some, these are all systems. Everything around us work as environments, so everything around us can be categorized into systems. There are many types of systems, right? But system is any systematic, arrangement of things. So first system is deterministic versus stochastic systems. What are deterministic systems? The outcome is fully determined by the initial conditions and the system's laws, right? So these deterministic systems, as the word deterministic shows, they are deterministic, right? Their outcome could be predictable, right? And there's no randomness involved, right? So this may seems like more abstract, but when you see it in your daily life, you can get it really easily. That, for example, we have a person selling fruits, right? So it isn't sure that, we aren't sure that at every hour there will be like 8 customers. Maybe at 1 hour there are 12 customers, at the other hour there are only 2. So this is randomness, and these randomness are stochastic systems, the seller-buyer system, right? But sometimes when, for example, you are in your classroom setting and you know that this is my first lecture and that the professor is going to come in and the next lecture starts at 9:30 a.m. and the following professor is going to come in. So this is a system, a deterministic system, where you predict the outcome, you know the things, you know the initial conditions, right? For example, they made a simple pendulum motion is deterministic if all forces are known and there are no external randomness involved influences. So these are more like abstract examples, but I gave you some real-life examples to learn that. Of course, the pendulum's motion can be deterministic if the forces are known. If they're not known, of course, we can't predict it. Okay, let's talk about the stochastic systems, right? I told you an example of a fruit seller or vegetable seller, and I told you that there's no really a way to determine, not a way, but there's no really, we cannot just say that there are going to be always 2 customers every year for this seller. Maybe sometimes the seller don't have any customer at all, sometimes he have a lot of customers, right? Um, but you can't say that for a system. For example, if there's a restaurant and it's really famous, right? Then you always can guess that there may be, more than like 10 customers always in the evenings at that restaurant. So this is more like deterministic, but it depends upon the laws, or the conditions the system have. Okay, stochastic systems involve randomness or unpredictability. Even with the same initial conditions, the outcomes can vary because the system is influenced by random events or variables, right? How can outcome vary? Because we have two customers coming in at 1 hour, and then we have no customers coming in the next hour. So now we can't say that they are fixed numbers, they are just varying continuously, right? And this can be presented with those really full distributions, but we'll talk about them later. An example would be stock market prices, which are subject to random fluctuations, right? They're always change happening. So understood that there could be random systems, and then there could be, systems which doesn't have any randomness, and they are deterministic. There could be like, if you read all of these systems, you may find that these systems are kind of correlated to each other. Maybe some the systems that are deterministic can also be discrete or, continuous. These are all going to be linked together. Then we have continuous and discrete systems. You have heard about this. Continuous means continuous in some interval of time, and discrete means that it is divided into some specific intervals in terms of maths, right? But we will simplify that too. So discrete and continuous systems, state changes occur in a continuous, manner over time, right? Variable change smoothly. For example, physical systems like temperature or fluid flow, they evolve continuously over time, right? So weather is continuous because it is changing, and it is changing continuously in a continuous manner, right? There's some interval here. So for example, for this week I had, for sunny weather, and then I have for the next day I have like cloudy weather, and for the next day I have like rainy weather. So this the week interval, it is continuously changing, and maybe it doesn't change. It may evolve in small intervals. Maybe in the evenings we have cold weather, in the mornings we have hot weather. So they're just intervals in which we are basically dividing the whole possible values term, right? Discrete systems undergo state changes at specific points, and this often happens in systems where events or transactions occur at a distinct interval, such as digital circuits or queuing systems in a bank, right? Queuing is a really important topic in the sense for the simulation system. Understanding it is really important. So, for example, the queuing system, maybe the one person was here, and maybe the second person was here, and maybe the next person comes in, and for example, if he was here at 5 a.m. and then he came at like 5 a.m. and then he came at like 5:15 a.m. So these are basically, it's not, you can't say that they are continuously changing, right? You can't say that this is 5:01, right? There's a person there. No, they are going to be changing at fixed variable intervals, right? Okay, so queuing systems are a good example, or digital circuits, where at certain points you have the bulb on, and at certain points you have the bulb off, right? Simplifying it a little bit. Then we have linear or non-linear systems. So they're important in the sense that they are often asked questions about. Linear systems. We are basically studying the classification of systems here. These follow the principle of superposition, meaning the behavior can be represented as a sum of responses to individual inputs. The relationship between variables is linear and can be described using linear equations. Nonlinear systems, they do not follow the superposition principle, and then small changes in initial conditions can result in large changes in outcomes. Chaos theory, and they are more complex and can show unpredictable behaviors, right? So really important stuff to note here. I want to change my color. So yeah, in the linear systems, we have this phenomena of principle of superposition. So What this is that, for example, we have, a bank here, right? And we want to understand it better. So, for example, a person is coming in at one instance, right? At one instance, maybe people are coming in 24/7, right? But and we can understand that the response to these all individual inputs can give us the whole idea of how the queuing system basically works for the span 24/7, right? So in the linear systems, you can get the idea from the individual groups, right? And you see that the reaction among all of these inputs is going to be same, right? However, for the nonlinear, you say that they could be changed at any point, which can cause a large outcome change, right? So means linear systems means that everything is going to be smooth, right? But the nonlinear systems means that any small changes could cause the big results, right? So this is a non-linear system. Linear means which really goes, smoothly, no offense, nothing bad, right? But the non-linear means that the superposition principle is not followed, that the small things cannot really predict the outcomes, that there some cannot predict the outcomes. Maybe some things can affect more about through the outcome, some things can affect less the outcome. And I think stock market could be an example of nonlinear systems because it really doesn't matter. We can't really say that there are some there are really responses to the individual inputs could really represent the outcome. There could be anything happening at any minute, right? Therefore there's a lot of randomness involved here, and so we can also say that stochastic systems can be nonlinear, right? But it's better to search for more examples to understand these two better. Open versus closed systems, so I'm also going to do that. Open systems, these systems interact with their environment, and closed systems do not interact with the environment, right? For example, exchanging energy, material, or information. Biological organisms are open systems as they interact with the surroundings, and an example might be a perfectly insulated thermos bowl, right? So for example, this is bio to understand better, and this is physics. So if you want to say that, physics, in always we talk about containers and jars and beakers, and then we have always chemicals coming up. So if I have like a flask, and I have a bunch of chemicals in it, and I have, close it with a cork, where there's some cargo where we say the cover, and then this is what we call as an closed system, right? But an open system would be like the organisms or all the plants around us who interact with their environment, right? But there could be more examples. Open systems is anything, right? Open systems are basically the interaction with the environment, like sun, like light. They are the systems, right? They all mix together to make a system. The closed system is anything. For example, you have a cooker in which you are just boiling something. That's also a closed system, right? Which do not really interact with the environment, not exchanging any material, any information, or any energy. Got it? More example in these two as well. Static versus dynamic systems. What are static systems? These systems do not evolve over time. Their state is constant unless acted upon by external force, like a bridge, or like where the system stays constant unless the load or structure changes. For example, this is a bridge that connects to, to, for example, okay, I wanted to make like these shape here, but this is a bridge that's like built to connect two cities from this. So this is always going to be the same unless some things come happen. For example, uh, some bad things happen like earthquake or anything else. But they're also going to be always going to be the same system. But the dynamic systems they change, and they are all represented using differential equation or other rules to describe their evolution. So we talked about The linear systems are presented using linear equations. And what are linear systems? They said that the individual inputs can be summed to make the overall behavior. And we said that the static dynamic systems can be represented by differential equation because they always change over time. And that's why you see this delta sign in differential equations if you solve them. So I messed it up, but it looks like this, right? Delta F or delta S means change in S, small change in S. And then we have those derivatives and etc., etc., second derivatives. That really works for differential equations. Like ecosystems where populations of species may fluctuate over time, right? So species may change, or even the dynamic systems could be the weather as well, because it's also changing, or the time is changing. It's not static, so it can also be represented using differential equation. Then we have what we call this lumped versus distributed systems, right? What does this mean? So lumped systems, in these systems, the state variables depend only on time. So what are state variables? We don't talk about them enough, but the state variables are basically in a system. So for example, in the simulation part, because you're simulating things, you're going to be assuming some conditions, okay? So in this part, you assume that the system can be off, it can be on, or it can be moderate position. So state variables are presenting that what is the state of the system right now, right? How the system is moving, which variable does it depend on? So in the lumped system, it depends only on time and are assumed to be uniform in space. An electric circuit can be modeled as a lumped system, right? So in a lumped system, what happens is you depend only on time and you have a uniform space distribution, right? So an electric circuit, which can be, for example, I would want it to be on for a certain time, and then I want the battery to be on for a certain time, etc. We have distributed systems. Distributed systems have state variables that depend on both time and space, right? For instance, temperature distribution in a metal rod over time would be an example of a distributed system where both time and spatial variations matter. So I think the best way to understand this is when you studied in physics the length concept. I think similar to that length concept, when we studied about a rod and we studied about its cross-sectional area, and there was some condition that if you have something like a big cross-sectional area, then maybe the length is also bigger, and if you have a small cross-sectional area, if the length is also small. I think it was some law that we have studied. So so when we said that the total area or the total cross-sectional of the road depends upon both the area and the length, right? So for these distributed systems, they depend on both the time and the space. For example, they are also giving example of a rod, so that we have a metal rod here, right? And the metal rod, and we are really, understanding the temperature of this metal rod, right? And now, for example, if I just give it a normal room temperature, it would be a lot different with when I heat the metal, right? So they say that the time would also would also be dependent, and the space will also be considered in the case of the distribution systems, right? Yeah, so this was lumped, where we only talked about the time, and we have a uniform space like in electric circuit. We don't have razor space matters, and the distributed systems we do have time and space. So these were the classification of the systems. We have studied 8 types, and in the next lesson we are going to study the system theory.